Ladies and gentlemen, my name is Maximilian Ogiela, I represent Team Poland. I'm happy to present to you our solution to problem number 6, non-contact resistance. The problem content states: the responses of an LRC circuit driven by an AC source can be changed by inserting either a non-magnetic metal rod or a ferromagnetic rod into the inductor coil. How can we obtain the magnetic and electric properties of the inserted rod from the circuit's responses? Now on this video we can see the view from the screen of the oscilloscope, which shows the voltage across our coil. We can see that through inserting the rod into our coil, the responses changes. First was the aluminum rod, now we can see the result for the stainless steel rod, and the last one is the copper rod. Now let's move on to our LRC circuit. It consists of the resistor, capacitor and inductor, and connected in series. And using governing equations, the first Kirchhoff's law, which states that the current flowing through each of the elements of our circuit is the same, and the second Kirchhoff's law that states that total voltage applied to our system equals to the total voltage drop across all of the elements in our circuit, we obtain the damped-driven harmonic oscillator equation, which solution looks like this. However, we can see that the part coming from the general solution is only relevant for small periods of time and will only investigate the steady state region in our case. Now, by knowing the formula for the voltage drop across the inductor, we can derive the formula for the amplitude ratio of the voltage drop across the inductor compared to the voltage applied to our system. And we can also obtain the formula for the phase shift of the voltage on our coil compared to the voltage from the generator. And here on this graph we can see theoretical plots for different values of the resistor used in our setup. Now we can see the results of our measurements for the amplitude ratio of the voltage across the resistor divided by the voltage from the generator. And we did the measurements for the coil without the core inside. And when we fit our function, we are able to obtain the inductance and the resistance of our coil that we used, which is really important for our further calculations. Now we can compare the results for the coil with ferrite core, and we can clearly see the differences. So let's think why. So when the current is flowing through our coil, it generates magnetic field inside it. And when the metal rod is inserted into our coil, it gets magnetized. So we can derive the formula for the coil inductance with a core. And there are three main magnetic properties. One is paramagnetic materials, for which the relative magnetic permeability is slightly higher than 1, the example is aluminium. Second one is diamagnetic materials, for which the relative magnetic permeability is slightly lower than 1, and the example is copper. And the last one are ferromagnetic materials, which relative magnetic permeability is significantly higher than 1, and the example is ferrite. From this we have a conclusion that only ferromagnetic materials interact with magnetic fields significantly. And by using our formula for the coil inductance with the core, we are able to obtain the value of the relative magnetic permeability for the ferrite rod that we used. And we can see that our function fits really well the measurements. Now we can compare the results for the coil with copper inside it. We can clearly see the differences. And even if we take into consideration the fact that the relative magnetic permeability of the copper slightly changes, we still see that our function doesn't fit match the results. So let's think why. So when the changing current is flowing through our coil, it generates changing in time magnetic field inside it, which, as we all know, induces the changing in time electric field, which due to the Ohm's law will create the currents inside our rod. And those currents, due to the Lenz's law, will induce the magnetic field in such a way that it counter-reacts the changes of the magnetic flux through our coil. And from this we have a conclusion that eddy currents are induced in our conducting rods. And in order to take them into consideration in our theoretical model, we'll solve Maxwell's equations for three main regions in our setup: rod, inside and outside. And we have a boundary conditions for the rod inside border, which states that there are no charge accumulated at this surface, and that there are no surface currents at the surface of the rod. And the inside-outside borders conditions are that there are no charge accumulated at this surface, and the surface current is caused due to the current flowing through the coils in our coil. And we can solve the equations, and we obtain the magnetic field distributions for different regions in our setup. And here we can see a theoretical plot for the low frequency, and we can see that then magnetic fields are constant in all of the regions. However, when we increase this frequency of oscillations in our circuit, we can clearly see the differences in the magnetic field distribution inside our rod. And here we can see our boundary conditions that we showed previously. And when we take a look at the magnetic field distributions inside our rod for different frequencies, we can clearly see a skin effect, which is due to the eddy currents induced in them. And as we could expect, for higher frequencies for which the eddy currents are stronger, the skin effect is also stronger. And that's why for high frequencies, magnetic field is mostly localized at the surface of the cylindrical rod. So we can calculate the formula for the voltage drop across our coil using the integration over the curvature of our coil, and we can see that this formula looks exactly the same as the regular formula for the voltage drop across the coil, with the change that our inductance is multiplied by some function dependent on frequency. However, this function will create our inductance to become a complex number and will be dependent on frequency. And we can see a theoretical plot of the real and imaginary part of our inductance. And when we substitute the real and imaginary part of the inductance of the coil into our equation, we can see that the imaginary part behaves exactly the same as the resistance of the coil. And this is the non-contact resistance about which is the problem content stated. And by using this formula, we can obtain the theoretical plots for the resonance curves in our setup, and we can clearly see that for the difference, for higher values of conductivity of the rods in our setup, the resonance frequency increases. Our experimental setup, it consists of the computer connected to oscilloscope and the function generator, which were then connected to our LRC circuit. And using the program in Python, we were able to control both the oscilloscope and the function generator. And then during the measurements, we didn't have to do anything. Now used materials in our setup. So we use the capacitor and the resistor for our LRC circuit. We use the different driving frequencies and different driving amplitudes using our waveform generator. And we use different materials of the rods that we were inserting into our coil. Copper, aluminum, stainless steel, steel, and ferrite. Here we can see the parameters of the setup that we changed and the values of them. Now we can compare our results for the different radii of the copper rods. We can see that our fitted functions fit really well the measurements, and from these measurements we are able to obtain the value of conductivity. We didn't measure the relative magnetic permeability, we assumed that it's around 1, because the changes from the 1 are so small that the accuracy of our oscilloscope is significantly higher than the changes of the relative magnetic permeability of the magnetic core, a copper core. Now we can see the results for the stainless steel, for which we were able to obtain the value of the relative magnetic permeability and the conductivity of our stainless steel rods. And again, we can see that our functions fit really well the measurements. The last one are the results for the aluminum rods. So we again assume that the relative magnetic permeability is around 1, the same as we did for the copper. And from these measurements, we are able to obtain the value of conductivity of the aluminum that we used. Now we can see the results for the different materials of the rods that we use. We can see that for all of them, our fitted functions fit really well the measurements. And we can see that for a strong ferromagnetic materials, such as steel and ferrite, the resonance frequency decreases. However, for the stainless steel, which is a poor ferromagnetic material and is conducting, the conductivity has higher effects. And because of that, the resonance frequency decreases, the same as for the copper and the aluminum, for which the conductivity are the only relevant properties. We can compare the results and the values of conductivities that we obtained from our measurements for different radius of the rods. And in order to check whether the values that we obtained are real, we used independent measurements of this. So using the high current generator and the multimeter connected to our rod, we were able to measure the voltage drop across our rod. And from this we were able to obtain the value of conductivity. Now we can see the comparison of our results from the LRC circuit measurements and from our independent measurements. And we can see that they match pretty well. Here is the same graph presenting the relative accuracy. And we can see that for the radius of the medium radius of the rods, we obtained the best results. It is because for the high radius of the rods, our solenoid approximation might not work the best. And for the smallest radius of the rods, the changes caused due to the properties of our rods are really small due to the surface comparison of the surface of the rod compared to the surface of our coil. To conclude, resistivity, magnetic permeability, and ferromagnetic properties of metals have impact on LRC circuit response due to the fact that metal rods are conducting and placed in changing magnetic field. We need to take into consideration eddy currents induced in them. Ferromagnets decrease the resonance frequency due to their high magnetic permeability, which increases the magnetic flux through our coil. And by fitting the resonance curves to the measurements, we obtained different values of conductivity and magnetic permeability of the rods that we use in our measurements. And these values can be seen at the bottom of our slide. Thank you.